Much, Ben and Emilia, for organizing, and thank you so much for the invitation of speaking here. I'll talk a bit about a beginner's-friendly introduction to diffusion models in JAX. So I'll talk about two things. First, the concepts behind diffusion models, and about JAX. A few words about myself. I'm a postdoctoral researcher at the Center for Astrophysics, and I usually research in the field of X-ray and gamma-ray astronomy, where I develop like new AI, machine learning, and statistical methods to analyze X-ray and gamma-ray data. I also do scientific open source software development. I maintain a package that is called GammaPy for gamma-ray data analysis. It's also part of NumFOCUS, so this is great. And I'm also editor for JAWS, or the Astronomy and Astrophysics track of the Journal of Open Source Software, which is also sponsored by NumFOCUS. So there's some great relations here. You can find a bit more about my work on my website and on my GitHub. But just to give you an impression, so the kind of problems I'm working on is something like this. So this is an image of a supernova remnant of the Chandra satellite. And it's very noisy because we are measuring X-ray, so we're really measuring only individual photon events. And everything here is really noisy and noise by Poisson noise and corrupted by Poisson noise. And we're looking for methods how to restore and denoise and sharpen the data. And this is one of the methods that we've developed. And you can see here the results. For example, here's a point source. Then that suddenly starts to pop up here after the denoising. You can see some structure, for example, here and here that really started to pop up. In this context, it's important to know about image priors. In this context, I started to learn a bit about diffusion models. I'm not an expert at all about diffusion models. So what I present here is like these things that I've learned in the past few months, maybe, or weeks. But at the same time, I also started using JAX, and I thought, okay, I would like to connect those topics. So the material for the tutorial is you can find it on my GitHub. I think, Emilia, you shared the URL. So if you would like to execute the code along, you can do the setup here. Otherwise, at the bottom of the README, there's also just this opening Colab link, and you can just open it in Google Colab and just execute along if you would like to. Otherwise, you can also just listen and watch. I think this is also fine. What are the prerequisites for this? Just roughly like 2 years of experience with NumPy and Matplotlib, so it's really mostly beginners oriented. But I will do a quick survey just to see like what's the prior knowledge of the people. So Python standard library, func tools, name tuple classes, and these kind of things. Understanding global and local scopes in Python, and then array operations in NumPy, random number sampling, 1D, 2D plotting histograms. And then on the ML and math side, I would say it's basically undergraduate level knowledge of ML and statistics and linear algebra, just a few things. I think most people are a bit, not really, but a bit older, so I think they have this. Okay, what are diffusion models, just in a single sentence or short paragraph. So diffusion models are a class of generative models that are based on the concept of like iteratively removing noise from images or in principle like any kind of data. They're not restricted to images, but like you can use them to sample from any kind of distribution. Generative means they model really a probability distribution, and they can be used to draw new samples from the distribution, and thus really, for example, generate new plausible images. And I think this is what made them really famous in the end. Or an alternative way of thinking about diffusion models is really to think of them as sampling algorithms, and they sample from a fixed distribution, where this distribution is defined by the distribution of the data you've trained the model on. But like a quick illustration of this, so it's easy to destroy data. So you have an image of a cute dog, and then you start adding noise. And this is a very simple thing to do. I think everyone has some kind of intuition on how to do this, just adding noise. But then diffusion models really try to invert this process. And if you look at this here, this really looks like uniform noise. And once you revert this process, you can actually recreate this image here and sample. And we'll learn a bit like how this works in more detail. In general, like the sampling from high-dimensional distributions, such as the distribution of images, is really hard and tricky because like each pixel represents like an independent dimension. However, diffusion models are a way to make the sampling process feasible and, most important of all, also like scalable. So in this tutorial, we'll take a look at a specific type of diffusion models called the denoising diffusion probabilistic models, and by now I think there are a few more variations, but this is, I think, like one of the most cited papers where the concept was introduced. I will mostly work on toy examples for illustration. So the goal is really to give you some kind of intuition how this works and really how the models works. We cannot really train like a full-fledged model because this is really, really expensive, but we can work on these toy models and really understand the concepts behind them. I personally find that diffusion models are to a certain degree misnomer because like the important part is actually reversing the diffusion. But this is just a side note. So in a single paragraph, what is JAX? So you can think of JAX as NumPy with support for GPU and automatic differentiation. So it supports hardware acceleration, and it also has also like built-in just-in-time compilation. So maybe you've heard about Number before, which is just-in-time compiler for Python, and this is also built into JAX. Then it also offers stuff like function transforms, for example, native vectorization. If you've used something like NumPy vectorize before, this is also built into JAX, but really like instead of having a Python loop as NumPy vectorize, it is really lowered to lower level code. And everything in JAX then is finally lowered to hardware accelerated XLA, and XLA code is an open source compiler code for linear algebra and machine learning. So the JAX documentation is here. What's nice about JAX is also that there's like a diverse ecosystem of open source tools built around JAX covering, for example, neural nets for deep learning. So just to mention some, Flex, there's Equinox, there's Keras. There are optimizers, for example, Optex and Optimistics. There are support for probabilistic programming, so sampling, MC sampling, BlackJAX, NumPy, and many, many others. There's a curated list of resources around JAX here in this GitHub repo, which is called Awesome JAX. Okay, so just a quick survey. Who has worked with JAX before? Okay, thank you. Who has worked with PyTorch and deep learning? Okay, these are much more people. Who has worked with diffusion models before? Okay, thank you. And if you're comfortable sharing, so like what is your experience level in Python? So 2 years of Python experience or less? Between 2 and 5 years? And more than 5 years? Okay, thank you. I've compiled a few more resources. Those are mostly useful for preparation, but also if you want to look into a few things in more detail, you can go to those. There's a really nice video series that really covers the diffusion models step by step. This is really one thing I can recommend. And this goes also a bit into the math details.
So sorry to bother you,
yes.
Axel, but do you mind moving the mic up a little closer to your
Yeah, sure.
just so that we can be sure it
Yeah. I'm trying to put it here.
Is the one that's going to amplify you to the room, that mic.
That one? Ah, okay, it's even working. Okay, I can try to speak a bit closer to this one. Yeah. Yes, thank you.
Sorry.
Yeah. Okay, if you work in a collab, then just uncomment these lines here and just to install the required dependencies. If you're working locally, then this should not be needed. So as a warm-up, we'll just take a look at the diffusion process. So diffusion you typically know as a physical process. For example, like when particles spread from regions of high concentration to regions of lower concentration over time. So an example of this would be you drop an ink into water and then it starts to dissolve. This is a diffusion process. Or for example, how heat is conducted in materials. So you have a source of heat and then the heat is spread using, or this can be described as a diffusion process. This is typically modeled as a stochastic process. Maybe you've heard about Brownian motion, for example, like particles interact with each other. But this is really like a physical or very common concept in physics to describe many phenomena we see in real life and in physics. In addition to this random motion in diffusion, there's also another term that is sometimes called a drift, or for example, advection. So there can be external forces acting on this particle. And this can be something like wind, for example, or a gravity-driven flow in water, or really if you imagine, for example, stirring, putting the ink in water and then starting to stir. These are the two important components to note about the diffusion. So we'll first explore this process on a simple, just very simple example in JAX. So let's start with the relevant imports here. I will try to execute this. I'm running locally on my machine. Yeah, this is running fine. If you work with JAX, then I think the most important import to remember is this one here. From JAX, import NumPy, SJ, and P. So this JAX.NumPy namespace can be thought of a drop-in replacement for NumPy. It was designed to be as similar as possible to the standard NumPy, and I think by now with the Array API, it's basically equivalent, so NumPy 2.0. In almost all cases, you will find the equivalence of a given NumPy function in this JAX NumPy namespace. However, just to mention it already, there's one important difference. Array objects in JAX are not mutable. This means in-place operations that you've known, for example, in NumPy, so something like this, you're indexing into the array and setting value to 3. This does not work for reasons that become clear later when we discuss the just-in-time compilation. There are a handful more of these differences, and those are documented in the short bits. Otherwise, I'll just explain them along in the tutorial. So for this illustrative example, we'll just work with a simple mixture of Gaussians as an initial distribution of the particles. I'll use particles and samples basically synonymously. And in JAX, we can just use the functionality then from this NumPy works namespace to define our model. So I'm defining here a Gaussian, just the usual definition. And then I'm defining a Gaussian mixture where I have the parameters of the two different components in another axis. And then I just sum those two Gaussian components, I sum them up. This you can ignore for now. This is needed for later for when we compute the gradient. And then I just define the norm, U, and sigma parameters, and I can just use this to plot what the distribution looks like. I think my kernel just disconnected. Let me just, so it's not showing the output. Let me just restart my. Just restart my kernel. No, it's not plotting. Not sure what's happening here. This is all gray out. Okay, I'll do the quick thing and just change to the collab. Oops. Okay. Sorry for that. Yeah. Yeah, it changed to a different editing mode. Yeah, no, there we go. Yeah, run anyway. Yeah, this just takes a second. Let me just execute those. Who's actually following along in a notebook or like locally or in a collab? Okay, thank you. Mm-hmm. Okay, this is like this toy distribution that we're going to work with at the beginning, so it's just like a simple or mixture of two Gaussians. Now we proceed just to draw samples from the distribution. As this is a Gaussian distribution, we can directly sample from it using built-in sampling methods in JAX. And those are found in this JAX random namespace. This is also very similar to NumPy. Maybe if you work with NumPy random. However, there's one important difference. So in NumPy, you typically work with a global random state object to define the state of your random number sampler. JAX uses a different approach based on random keys, and those keys are split locally. The idea behind this is that if you want to distribute, for example, computations across multiple processes, then you cannot easily share a global state. But if you have something like this key-based thing, then you can locally split the key. And this makes the computations then in the end much easier to distribute, for example, across multiple processes and GPUs. The way this works here is, so you define the random key, you define the number of samples here, and then you can just draw from a normal distribution, you pass in the key, and you pass in the shape of the output. And then you can draw this initial set of samples, and if we make a histogram of them, you can see it's basically exactly what we expected. Now let's introduce the actual diffusion process. The diffusion process here we choose here consists of two distinct steps or terms. And the first one is really add noise to the sample by adding a displacement drawn from a Gaussian to each of the particles or samples, with typically a Gaussian mean of 0 and a variance defined by this beta t value, and this corresponds to the random motion of the particle. So really think of it as Brownian motion, for example. And then there's this drift, which is like a uniform or applied displacement that is applied uniformly to all particles or all samples. And this makes the particle here move towards the origin by applying with a constant factor given by square root of 1 minus beta. And this is basically equivalent to an external force acting on those particles. What we assume here in addition is that this beta is between 0 and 1, and that beta goes to 1 with time. The choice here is a bit specific and a bit magic, but I think you can at least develop some intuition that if you do this, so if beta goes to 1, then the variance will go to 1 with time. And if beta goes to 1 is at this term here, then you can see the mean will go to 0 with time. So I think this is very easy to understand. It's still a bit magic, but there's a more detailed reasoning of why this choice makes sense. So in addition to leading to the convergence, then finally to unit Gaussian, it also allows for computing the time steps like in a closed form. This is something we'll see later, and the actual reasoning is given in this DDPM paper. For now, we just assume that this is a good choice. And we can actually implement this diffusion process here. I've just chosen a Python loop. This is, I think, the simple and naive thing to do for now. So we set up this range of beta values varying between 0 and 1. I choose or use the x init values that I've drawn before. I define the number of iterations here, and then in each iteration, I vary the beta value. I do this random splitting of the key, so I start with a single root key, let's say, and then in each iteration I split it, and then I can use the key and the subkey. And this key here becomes the new key for the next iteration, and the subkey is the one that I use for the actual random number sampling. So here I'm drawing from the normal distribution, multiplying with beta, and here with the mean is shifted with square root 1 minus beta. And then I'm appending this just to a list, and finally I'm stacking everything to get something like a trace, how these samples have changed with time. This is then helpful to visualize this, how the diffusion actually changes the samples with time. And to visualize this, we can make a histogram. Of course, we could just use, again, a Python loop, for example, and call NumPy histogram, and then like do this for each of all the time steps. However, we can use already or introduce one of these function transforms in JAX. So JAX provides a few built-in so-called function transforms that act on basically arbitrary functions. An important one is called a VMAP, or JAX.VMAP, and what this does is basically equivalent to NumPy vectorize. So it applies, or also like similar to the built-in map in Python, it applies a function over the leading axis of an array. The main difference with regards to comparing to NumPy vectorize is literally that NumPy vectorize is implemented as a Python loop, while as in JAX, this is actually lowered to hardware accelerated code. So it's not a Python loop, and this makes many things in the end much more efficient. Here I'm using it to make the histogram function here to map this over the leading axis of our sample trace. And I'm defining or using here partial to define what I would call like my default histogram method. So I'm using 100 bins. I'm defining some range here and say it should be a density. And then I do what I would call like a batched histogram. So I'm applying the histogram to each time step, where the leading axis here then is the time. And this is then my batched histogram function. So I've magically converted this one-dimensional histogram function here into a two-dimensional histogram by leading over, or by mapping over the leading axis here. If we actually want to use this for visualization, I've just implemented this little helper method so we can plot the trace of the diffusion process here, where I'm using the batched histogram method here as a first thing, and then I can actually use imshow to illustrate this. And this gives a plot that is also, I think, one of the leading plots in the DDPM paper. So here you can actually see what's happening. So samples start at the position of one of the peaks in the original distribution, and then the mean moves towards 0, and then they just like wiggle around in this like stationary state in the end. We can easily convince ourselves that this final stationary distribution is indeed a standard Gaussian, just for illustration. So we make a standard histogram and compare it to a unit Gaussian. This is exactly what we wanted. Now that we've destroyed this initial distribution, this two-component Gaussian with the forward process, I think it would be great if we could reverse the process. This would give us a sampling algorithm that allowed us to sample in principle from arbitrary distribution or this distribution that we've worked with. And we would start from a normal Gaussian distribution. This is what we ended up with in this forward process. And then we would transform the samples back into the shape of the initial distribution. It turns out that such an algorithm exists, and this is named Langevin dynamics. However, the algorithm requires one additional piece of information, and this is called the score function or target function. So the score, or the score of the target function. The score function is defined as the gradient of the log of the distribution. And what's nice now in JAX is we can actually directly get the score function by taking the gradient of the log. This uses another function transform in JAX, which is called JAX.grad, and applied like a very, and the grad applied basically to any function will return the gradient of this function with respect to the parameter that you put in. So defining this for our problem here, so we define just the log of the Gaussian mixture model here. So I'm defining this little helper function that returns the log of it. I'm using here again partial. This is very convenient because then like it simplifies the parsing of the parameters later here with the JAX.grad. So I'm passing the norm, mu, and sigma parameters that we've used in the beginning. And then I take the gradient of this GMM log, and I also VMAP over it. The reason there is that, as you can imagine, that the gradient or something like a loss function should actually return a scalar value. And then you VMAP over this, and then you can do this for multiple values at the same time. This is what it looks like. So this is what the score function of this Gaussian mixture model looks like. Now we can implement this reverse diffusion process based on Langevin dynamics. And we start from an initial sample, and the algorithm looks like this. So for each, or starting from an initial estimate, we take the gradient of the log, so the value of the score function, and then we add, again, a random update. And again, we scale it with time. So here's this alpha parameter, and previously we called beta. So this is a bit of a funny thing. It actually has like fundamentally like the same structure as the forward process. And I think if you probably do some math, then you would find out that like this forward process that we had before would actually involve the score function of like a unit Gaussian or normal Gaussian. This roughly makes sense. And again, here for this random motion, we draw from a unit Gaussian, and we let alpha go towards 0, and we assume that we have infinite time steps, but it's just like, in practice, it's just like a finite number of time steps that are sufficient. There's another intuition behind this algorithm. If you take a look at this, and if you're familiar, for example, with model fitting, so what you do, for example, for maximum likelihood estimation all the time is you define some probability, or you define a likelihood, you take its log, and then you do gradient descent. So you compute the gradient of the function, and then you do gradient descent. And this is actually very similar. So this part here is just gradient descent, and alpha would represent the learning rate. However, if you do this, then all the samples would up at the maximum of the distribution. I mean, this is what you're looking for with maximum likelihood estimation. And to prevent this, you do two things. The first one is you add this random update. And the second thing is that you let the learning rate or this alpha parameter here go to 0, meaning you will not actually optimize until the end, let's say. But this was shown that this actually then converges to a posterior or to your target distribution in this paper by Max Welling et al. Now, we can basically implement, just slightly modified, the same process as we've done before. But I will show you one other little thing in JAX, and this is called the JAX-lax.scan. And this allows you to scan a function over the leading area axis while carrying along a state. And so what I've done here is I've rewritten or replaced the Python loop that we had before by what I would call like the body of the loop. So this includes a single update step. So this is really equivalent to the body of the loop that we had before. So I'm computing the alpha parameters here. This is just one specific parameterization as a power law here, where the alpha parameter goes to 0 with increasing index. Then I'm doing again just this random splitting. I'm drawing this dx or this random update from a normal distribution, and then I'm computing the score based on this x argument here, and then I'm adding the random update, and I'm scaling with the alpha value here. I've made one little change here. So there's a number of arguments to be passed to the function. So I could have just defined them here. So there's the key, there's the index, there's the x, and the alpha values. What I've done instead here is I've used the name tuple just to group them into the same namespace that I've called the args. The reason is just that JAX actually natively knows how to handle what are called pi, or what they call pi trees. So JAX knows how to handle, alternatively you could call it like structs of arrays. So really like hierarchical data structures of arrays. And if you would apply, for example, if you imagine, for example, having a loss function, and you pass in the values of the parameters as a dictionary of parameter arrays, and then you apply JAX.grad to it, what you would get back is a dictionary of the gradient of the parameters. And this is really, really convenient. JAX has built-in support for named tuples, for lists and dictionaries, but there's also the possibility then to register your own pi trees. So this, I think, is really, really convenient. Just another, not really detailed, but like important concept in JAX here is the concept on pure functions. So what I've done here is I'm using this little scan helper method, and internally the body of this function here in scan will be JIT compiled. So this will be passed to the JAX JIT compiler, and this requires functions to be pure, or what is defined in JAX as pure, or alternatively you can say they cannot have side effects. Meaning if you have arrays that are passed to this function, they cannot be modified in place. And the same goes like with other things that you pass in, they just cannot be modified in place. Or for example, if you would have a print statement here, this would also be considered a side effect, like a standard print statement. And the reason is really just to keep the JIT compilation simple and to have like these well-defined namespaces, or well-defined, we'll call it, well-defined namespaces. I mean, you can imagine, for example, if the code is, for example, JIT compiled or lowered to GPU accelerated operations, and you would pass in a Python object here and you modify it in place, then you would need to have some kind of communication between the GPU process and the main process, and this is just really complex to handle. And JAX on purpose try to avoid this, and hence introduce this concept of what's called pure functions. This has a few things to consider. For example, if you would like to print something in JAX during runtime, this does not really work. So if you do something, for example, like in Python here, and just say like I want to print the value of dx, then what's happening is, actually, let me just execute this. Yes. Then you can see it prints something, and this is what it prints. But it's not what you expected, I guess. So you're used to seeing the actual values in the array. However, for this you have to understand a bit better like how the JIT compilation works in JAX, and the way it works is it puts in what they call a tracer, and this tracer knows about the D type and the shape of the array. And then the actual Python code is only used to define the computational graph. And this means the Python code is only executed exactly once to build the computational graph, and then under the hood it's compiled just in time and lowered to XLA operations. And then once the function is called the next time, so the function or compiled function is actually cached, and when it's called the next time, then this compiled function is actually executed, and the Python code is never executed again. That's why we only see one print statement here, and we see like this traced function here. Just for you to know, so if you would really like to, and this is what's called trace time in JAX, so really tracing the operation, and runtime, this is like the actual execution then of the compiled code. If you would like to print the actual values here, you can use jax.debug.print, and this uses like this Python syntax, or like a bit old school Python format syntax here, like this. Can you say it? Yes, sure. Mm-hmm. Oops. So I've just replaced this with this JAX debug print statement. And then if you do this, you actually get what you would expect. So it's just something to keep in mind. OK, let me just remove this. In practice, you will find that JAX is very strict. So if you define a function that has side effects, then JAX will let you know about this. In practice, sometimes it can be a bit tricky to actually find out why this introduces a side effect. But the most common ones I've just mentioned already. OK, then we can use this scan method here to come back to our diffusion or reverse diffusion process. So to actually execute it, let me just talk about this. I'm again defining just the key, splitting the key. I'm defining the initial arguments, so the initial distribution and the values for alpha and this P0 here. And then I'm using this jaxlax.scan to sample given the score function that we've defined before. And then if I plot the trace, then you can see this is actually the inverse process to what we've seen before. So this time we've started from a uniform Gaussian distribution, and then we're using this Langevin dynamics sampling to transform our samples into these in this Gaussian mixture model that we've defined using the score function. This we can just quickly verify that this has worked really nicely just by plotting the histograms. When do we aim for the break? 8:30? Yeah, okay. Yeah. Okay, so we've transformed the samples from the unit Gaussian into the target distribution. Yes?
I guess I missed what were the iterations to it. So why is it only in the end the proper distribution you want to have, but why is it in the beginning, why is it the original Gaussian? So what's happening over iterations?
Sorry, can you just come? Yes.
In this plot,
Yeah.
in the beginning it's just the Gaussian.
Yes.
Then in the end it's the two Gaussians
Yes.
you want to have.
Yes.
What's happening is a function of iteration.
Yes. Yeah.
So what is happening? So
Yeah. Okay. Yeah. So there are two. Yeah. There are two things happening, right? So if you have a particle or a sample starting here at time 0, then the particle gets moved with these two terms in the diffusion process. So the first one is it gets moved or it follows a gradient, and the gradient is the one of the score function, right? And the target distribution is this two sample or two Gaussian. So this will shift the mean of the particle with time. This is one thing. And then the second thing is really like this random motion along this trajectory. And this will make sure that you really have, or that the particles really spread like over this density here. And in this case here, like most of the stuff happens here in the beginning, and then later nothing happens anymore, but this just tells you it's a stationary process. So it will converge at some point, and then you've reached your target distribution effectively already after like 200 iterations. I hope this clarifies it a bit better. Yeah. But it's literally the same process as we've used before to destroy the initial distribution that we had. Now, this was just a toy example, and especially one where we've known or defined our score function analytically. So we've defined this Gaussian mixture model and computed the score function. However, in practice, you basically never have access to like an analytical description of your distribution. So this gives rise to a topic that is called score matching. So instead of getting like this analytical description of the score function, you try to model it. And the initial idea of this, I think, came from a paper here by this guy from Finland, like Hivarin. And the idea is, I think, just intuitive. So instead of having something like a maximum likelihood, what you do is you define a loss function where you try to minimize. So here you have a model, and here you have the score function of the data that you're actually computing. And you try to minimize, basically just using a mean squared error loss, the difference between the actual score function and some kind of model that is up to you to define. And typically you would use some kind of neural net nowadays or deep learning approach to model this. What's interesting about this little expression here, so if you really do the math, so if you compute the expectation over this, and then I think you can use some integration by parts and something like this, you can show that this is equivalent to a different loss function that is shown here. If you're interested in this exact mathematical derivation of this loss, then you can check out this link here, for example, where Yang Song derived this a bit more in detail. However, this we can actually use to now model a score function. And for this, we will use a slightly different data set that is called the Swiss roll data set. And we will use, for the first time, some deep learning framework in JAX. I've personally, so there's a number of them available. I think the most important ones are Flax, or one named Flax, Equinox, and Keras. I've chosen Equinox because I think it's very simple and like I personally like it, let's say. And we also need some optimization routines, and those are available in OptX. So let's just take a look at the data first. So this is the data set that we are working with. So this is just a two-dimensional distribution. However, you can see it has a fairly complex shape. And the question of how to sample from this is not as easy to answer. So to model the score function of this data set here, we can, for now, just use a simple multi-layer perceptron. In JAX, as I said, like there are multiple choices for deep learning. I found Equinox the easiest to work with. If you take a look at what the model definition looks like, for example, in Equinox, if you know PyTorch, and I think most of the people said they do know, then this will look very familiar. So the definition here of a model or a module is by inheriting from equinox.module. Then you have some initialization where you initialize the parameters and the structure of the model. And then you have to define the forward pass, and by convention, this goes via the underscore call function in Equinox. Otherwise, I think this is very, very similar. The differences are in Equinox, you have this additional declaration of the members here as on the data level. This is borrowed basically from the syntax from data classes. But under the hood, Equinox will use some of this information then to make it easier communicate with JAX. And then the other difference, what you would not have in PyTorch, is this random number splitting, but this you've seen before by now. So we're defining this multi-layer perceptron to model the score function. Yeah, one additional comment. So, and this is specific again then for JAX. So if you work with PyTorch, then typically your first axis in all your data here is the batch axis. And you will execute the same model over all entries in the batch axis. This is something you don't necessarily have to do in JAX because you can actually VMap. So you can apply this model over the leading axis of your arrays. And this is the design choice that was done in Equinox as well. Other libraries have other design choices, but just for you to know. So in Equinox, you never really have to handle a batch axis. What you do instead is you define your model. You don't care about the batch axis. And then in the end, you call jax.vmap, and you pass in the model. And then it's automatically mapped over the leading axis in your array, which is typically the batch axis. So this is possible because Equinox modules are these structs of arrays or PyTrees. However, there's one thing to keep in mind with PyTrees. I think this is one of the short bits as well. These are really trees and not graphs, meaning that a node in your model or a node in your hierarchical data structure, or like cannot be repeated, right? So they can only be childs, and this is equivalent to sharing parameters in a model, right? So in some cases you want to share the exact same parameter, for example in PyTorch, and then you would just point to the same object in memory, and this would make the parameter be shared. This is a bit more complex to achieve in JAX, but there are ways to work around this. The first one is you can use flags, or a newer development within flags is called NNX, and this actually supports graphs of structures or array structures. Or in Equinox, there are a few ways to handle this, meaning typically what you would do is you copy the model and then you replace the parameters or the parameter arrays that you would like to share. But there are many examples in the documentation. We have not seen this explicitly yet, but in this case, we can actually use JAX-JIT to do the just-in-time compilation from the score matching.
What's called denoising.
We have used it implicitly in the scan function.
Models, or sometimes
here we do it
DDPM.
Explicitly once.
It
so
works
the exact same way as you would use
previous approach
numbers
with the score matching.
This was not bad, but it has multiple problems. So, for example, in this score function that we've used and that we've optimized, there's for example a really large trace we need to compute, and this does not really scale. And then also the sampling process in the end got stuck, for example, in regions of lower probability. So where it's just like a very weak gradient, and then over time there's just not enough drift, let's say, for the samples or particles to end up in the right region. So how can we, and in the end this caused to miss details, for example, of the distribution. So how can we improve upon this? And the answer is really like this DDPM or diffusion model approach. It has multiple aspects, so we can make multiple changes, but I think the most important idea is here that you can make the model of the score function. This was right now, in the previous approach, it was static with time, so it did not change. What we can do is we can make it dependent or conditioned on time, meaning this vector field where all the particles move along will actually morph or change with time and provide more guidance, let's say, to all the individual samples to end up in the regions where we want them. So, but how does the training of such a model look like? And this is where this forward process comes in again that we've seen in the beginning. So we really create these diffused versions of our training data, as we did above, and then we make this change with time and move or morph it from the simple Gaussian to much more complex target distribution. Practically, there's another small modification we can make. So we had this beta parameter that changes with time. However, to arrive at a certain time step or the diffusion at a certain, or diffused samples or data at a certain time, we needed to compute all the previous steps, and this is a bit inconvenient. However, you can show that for this parameterization that we've chosen before, that you can actually compute or directly compute in a closed form, because all the updates are basically Gaussians. You can compute in a closed form what the diffusion model or the diffuse process looks like after a given time. And this was done also in the DDPM paper, so the math is in the appendix there. for now, we just take the result here. So if you have the diffusion at a given time t and 0, then you can directly compute it using this formula here. So this is unit Gaussian, this is the alpha bar t, and this is the square root of the alpha bar, and alpha bar is 1 minus beta to the power of t. In addition, we have this alpha, which is 1 minus beta, and the beta corresponds to the beta that we had before. So let's just define this range of beta values and compute the alphas and alphas bar. And this is really just the cumulative product, so this is just another NumPy function, or JAX NumPy function that we can use. And then we can use these alpha values to actually diffuse our data. I will straight go to the visualization because I think then it becomes clear what's happening. So this is the data set. At step 0, it looks exactly like the data distribution, like the initial data distribution. And then the particles here, or the samples, diffuse out with time. So the distribution here becomes broader and broader, all the structure gets lost, and we end up with a single unit Gaussian in the end. This is like the exact forward process that we had in the beginning. And we can quickly just verify that we really end up with a unit Gaussian, so the marginal distributions of this, so projected along the x and y axis are unit Gaussians. Just a little thing to mention here, so JAX also has a SciPy namespace. However, the SciPy namespace is incomplete. So you might find some of the SciPy functions and some SciPy namespaces, you might find them in JAX, but not all. One that is fairly complete is the stats one. So if you have worked with stats distribution in SciPy, then you will find most of them in JAX as well. Other things, for example, like ND image or signal, this is fairly incomplete. But you can find in the JAX documentation, there is a document outlining the reasoning, which parts have been re-implemented in JAX and which haven't been, and which were out of scope. Amelia, you want?
Yeah, sorry to interrupt, Axel, but I was just curious, and sorry if you explained this and I just missed it, but what is the relationship between the plot that is right before the break, it looks like it was diffused a little bit in the sense, yeah, that, and then the step 0 to 24 that is a little bit down that we just.
Yes, yeah. So this plot here, I mean, this looks a little bit diffused, right? But this was the result of us trying to sample from the distribution, right? So the distribution that we are working with is just this toy distribution. So this is the original one. This is the actual data that we were working with. And then we've tried to model the score function of this distribution here using this score matching approach. And this gave us the score function of the distribution, and then we've used this Langevin sampling approach that is also shown in the beginning of the notebook to actually sample from this distribution using the score function. This kind of worked. So the samples, or the final samples that we ended up with, looked like this, but we missed these details here of the distribution, and this is something we would like to improve upon. And this is done using the denoising probabilistic models. And the additional step then that comes in, so instead of modeling the score function of this distribution in a static way, we model it what I would call in a dynamic way. So we let the score function change with time, and this is illustrated here. So what we will do then is not compute a single score function, but we will compute a score function for this step here, one for this, one for this, one for this, one for this. And then we will end up with a much more guided or principled approach or way of sampling from this distribution. So just to verify, in the end, we ended up with this unit Gaussian distributions here in the final step. So this is really like a two-dimensional unit Gaussian. And then we modify this MLP that we've used to model the score function to be dependent on time or dependent on the time variable, or in this case, just like the index. So we're using a discretized time where the index in the number of of iterations just represents like the process with time. A very general way in deep learning to represent, for example, a time or make a model dependent on time is just using an embedding, or what's called an embedding. And the embedding here literally just corresponds to a matrix which has a number of entries. And in one axis, it has the number of time steps we're in, and then in the other axis, it has the number, in this case, of hidden parameters in the MLP. Then we can access the embedding at a given time. So this is what's happening here in the forward process. And then we can just multiply the out value after we've applied the first linear layer. And this will, like, if you will, like modify the values then given the time. And the embedding is typically learned at the same time as the other parameters of the MLP. But this is one way of making a time-conditioned linear model. There are other ways. For example, sometimes people will use like these Fourier descriptors, so having like the sine or cosine embedding. I think this is very common in natural language processing and transformers. But this embedding here just works fine. So I'm defining this time-conditioned linear model. It's really just this linear model with the addition of the time embedding. And then I'm redefining this time-conditioned MLP. It's exactly the same MLP as before, except that I'm using this time-conditioned linear. But you can really think of this as having an MLP at each step in the forward process, or a different MLP. In the training, we apply one more additional modification. So we define the model and loss function such that the model predicts the noise in each step. The math is a bit more complex for this. So we're using the MSE loss here, and the MSE loss is between the prediction or noise prediction of the model and the actual noise that we've sampled here. The math is given, for example, or shown like very nicely in this one YouTube video that I've linked above, where you can show that this actually corresponds, after you've done a long range of math, to maximizing the likelihood that a sample comes from a given distribution. But for now, I think we just have to take this result here. But intuitively, so the model is trained to predict the noise in each step. And then in the sampling process, we can just subtract the noise from the current iteration and then get like a less noisy version of our data or the image. And this is exactly what was shown in the beginning. And then if we do this iteratively, then we finally arrive at a denoised sample of the data distribution. And this really matches the process that we've illustrated in the beginning. Okay, let's do this. So we are setting, in this case, or increasing the number of time steps. I'm just using 100. 25 might work as well, but this is fine. I'm defining the betas and alpha values. I'm defining the time-conditioned model. Let me just re-execute this. And then I'm defining this MSE loss here. I have this make step function. It's, again, exactly the same as we had before when we just fitted the MLP. Has the same structure here. And then I've just modified the training loop here with two things. So instead of always passing in the same X, we pass in the diffused X. And the way we do this is that in each iteration, we draw like a random time step. So we say we would like to model like time step number 1, 3, 5, whatever. So the ones that I've shown before. And then we compute what the diffused data would look like at this time step using the formula with the alpha bar and this square root of the alpha bar here. And then we condition the model also on the same time step. So this will tell like which MLP to use at the given time step. And this is just randomized, and then you can show like once we randomize this that this also like minimizes the overall MSE. Again, we're using the random splitting here and have this additional noise for the diffusion process. Then we can let this train for a certain number of iterations. Just on a side note, if you work in the Google Colab, I mean, you might actually use a GPU accelerator. So if you do this, or if JAX finds some kind of GPU or TPU accelerator, then it will use this typically as a default. So the same code here will just work then or be executed on the GPU if it's available. But if you would like to have more control, then JAX arrays, once you create them, have a device attribute, and then you can declare like on which device the arrays should be executed, should be created. So this is very similar, for example, to PyTorch. Yes.
Have you tried programming in Julia?
No. So the question was whether I've tried programming in Julia,
Yes.
and the answer is no. I mean, I know Julia and know some concepts, and I've done a little bit of programming like in the tutorial, but I've never really used it. I mean, typically what I've seen is that conceptually, I mean, you cannot really compare JAX to Julia, but conceptually, JAX works on structs of arrays, while Julia supports array of structs. I hope like this difference makes sense. In the end, for example, there's a really nice blog post by Patrick Kitcher. So he's the main author of the Equinox library, and he's given some reasons why he has decided like to put his bet or like work on JAX instead of Julia. But I think the main reasons were not performance, but just like the state of the ecosystem and the state of the standard library. But I can search for Patrick Kitcher or search for Equinox and go to his website. I think he has a blog post where he outlines some of the reasoning. Yes.
So instead of a one-step process where we go from essentially random noise, capturing random noise,
Yes.
to score-based,
Yes.
slightly less noise,
Yeah.
right? We are doing this now so that our, like the vector field that you showed in the original case, the vector field has really sharp ridges because of our data
Yes.
sets.
Yes.
The goal is to kind of avoid those sharp ridges immediately on, and in fact, slowly kind of go into what the final distribution looks like in small time steps. Is that the core idea?
This is exactly the core idea, and this is exactly what I'm going to visualize in a second once the training has finished. It's much faster locally on my Mac. When I execute this on my M1 standard thing, it runs like in 40 seconds. Right now, this is running without any GPU acceleration, I think, in the Google Colab, whatever processor they have. I don't really know. OK, now it's finished. Yes, so we finished the training. And what you can see is that really for each time step now, we have a different score function. And this is exactly what is visualized here. Let's actually start from the last step here. It might be a bit hard to see, but the score function here is really, you take a look here, and then there's just like this single, sometimes it's called like a sink. This is where like all the particles would go to, so they will all go to the center. And then this gradually changes. And then once you go come, for example, to step 14 and 13, then you have more structure in this score function and more details. So like the vectors are now going towards the direction of higher probability, and you start to have these structures here. And then like in the final step here, you have the details of the score function really point towards the details of the distribution here. But really the overall idea is indeed like instead of having like this single step approach, you break it down into smaller steps. And this is really equivalent to having the score function depending on time, where the time dependency is encoded by this forward destruction process. Then we can use this time-dependent score function to sample from the model. It's basically just a slightly modified version of the Langevin sampling. So this is almost exactly the same code that we've used before, except that instead of having these hyperparameters in the Langevin sampling, I'm using these alphas and alpha bars that I've computed before. And then I'm using this partial here to condition the model on the time. In principle, also in JAX, I mean, it could be passed into the model as well, but I find this a bit more elegant. And In this case, for example, it's easier with the broadcasting because index is just a single number here. But this step here is really then equivalent to the Langevin part. And then I can use this to sample from the distribution using this time-dependent score function. And let's visualize these sample, and this is what I arrive at. And now this time, like the details of the distributions is present. So this is not perfect, but still it is better than the part that we had before. Let's just make this little animation of the trajectory. So this is the initial distribution that you start with, and then you can see how the particles move around and then really clump together in these high density regions of your distribution. So this is really like how the process evolves with time. So this looks much better than the earlier attempt. And this is basically all that you need to know about this or understanding this diffusion models or diffusion process. So the main advantage of diffusion models in general is the sample quality and the accuracy of the sampling. The main disadvantage is really that the sampling is rather slow. So what we've done in the last step you've seen is we've replaced like a single evaluation with basically 100 evaluations of the model. And for real diffusion models, these steps can be up to, I don't know, like up to 1,000 or more. This makes them really, really expensive to compute. However, like the image quality, for example, that you get with image sampling is really, really high and really, really good, and you can really cover like a whole or the whole data distributions. If you take a look then at like real diffusion models, so the one that really sample from images, there are a few smaller differences to keep in mind. So they're really for higher dimensional images. We've worked with 2-dimensional data now. For images, it's really like every pixel is an independent dimension. And then instead of this simple multi-layer perceptron, typically diffusion models use time-conditioned unit architectures. So this is an architecture that has proved to work well. But you can literally, like in this training loop that I've shown, you can literally just exchange the model part and everything else will remain the same. And then there are different ways to schedule how the variance changes with time, and some are more optimal than others. What is very common for these larger scale diffusion models is a cosine schedule, for example. And then, of course, scaling this up requires handling GPUs and these kind of things. So this is not something that I've really covered in JAX, but I will make at least one comment. So the way how distributed computing works in JAX is a bit similar to how it works in Dask. So you have a single array object, and then you can distribute this single array object across multiple processes and multiple devices. But in your Python code, it basically looks like a single array object. And then there are other smaller things, like it's common practice to use exponential moving weight averaging during training and these kind of things. So here's some links with larger scaled implementations, so you can take a look at those. And those are really meant to sample nice images. There's also, as a final comment, there's a nice connection between diffusion models and stochastic differential equations. So instead of this discrete time handling that we had, one can actually handle the time as a continuous variable and then use standard ordinary differential equation solvers to handle the sampling process. There's, for example, one example here in the Equinox documentation, which I think is really, really nicely done. Okay, this concludes the tutorial. I hope it was useful. I hope you understood like the main concepts behind diffusion. So what's the forward process? What's the reverse process? Also that really like the score function is dependent on time. I think this is the main takeaway. I hope you learned a few things about JAX. So most importantly, in many ways, you can just use it as a drop-in replacement for NumPy. But then you have these more advanced things like function transforms for gradients, for VMAPs, and these scans. And most importantly, you have just-in-time compilation. I can really recommend to try this out and see how it works for your problem. So thanks a lot for the attention. I hope it was useful. If you have further questions or comments, you can just open an issue in the GitHub repo or just reach out to me via the contacts of my webpage. Okay, thank you. Yeah, there are more questions.
Yeah, so just broad question. I recall most people
Mhm.
repository, and he chose JAX because of ecosystem support. I want to hear what's your reason for going with JAX versus PyTorch, especially if you're generating things like MCP modules.
Yes. Yeah.
I feel like it could be a little easier technically with PyTorch. It also has just-in-time JIT since 2.0.
Yeah.
So
Yeah.
I just want to hear your pros of JAX over PyTorch.
Yes, yeah. This is a very, very good question. There are multiple things to mention here. I mean, the main reason in the beginning for JAX is really the just-in-time compilation. And as far as I know, it was only introduced in PyTorch, probably because JAX or existed in JAX. And then I think conceptually, or like in their design of the code, I mean, JAX is simpler in the sense that they've decided like all the code is lowered to XLA, and this is just like a single, basically like this single lower level language that you use, and there's no other thing that they support, which I think makes it a bit more stable. I think what's intuitive is really like these function transforms, so something like a VMAP. And there are a few others, but this comes a bit like if you prefer, for example, functional programming. So it's a bit of a matter of a taste, I would say. So then this comes in handy typically, and I think this is something that you will enjoy. PyTorch, I think, is easier if you really come from the object-oriented part of Python. At the same time, I think in terms of, for example, code maintenance and code stability, PyTorch has a harder time of maintaining these kind of things. Also, for example, I think in the JIT compilation of PyTorch, I mean, you can have a global state in this, but this is like much more harder work. On the other hand, for example, this is something that I haven't shown extensively, but with JAX, as you have this native support for PyTrees, this gives you basically some kind of object-oriented interface to JAX as well. And this is shown with Equinox and these modules. By now, I would say, I mean, you can check, so there's Keras, right? And Keras allows you to choose the backend. And as far as I know, I think typically with a JAX backend, you reach the slightly better performance. And I think this is really just due to the fact that everything is JIT compiled, and you just have this single compiler that takes the whole computational graph and then starts to optimize it and lowers it to machine code. So this is what I've seen. Otherwise, I would say it's mostly a matter of taste. So if you're more on the functional programming side of things, you might prefer JAX. If you're more really like on the object-oriented side of things, you might prefer PyTorch. Yeah.
So a lot of this is new to me, and I think I followed that. So thank you very much. The score function, I think you said it's kind of like curve fitting, and in curve fitting, that'd be a bunch of different well-understood curves that you could start with. So you have the Swiss roll one. Is there a set of well-used or well-understood things that you would use for score functions, or is that something you just have to kind of figure, guess from your data set? Can you repeat the question?
Yes, yeah. So the question was whether there's like, just from experience, like a well-defined set of models you could use to model score functions. And the answer is no. I think score functions can be as complex as data. Meaning typically what people use is they use any kind of neural net. And there's no difference in complexity, let's say, if you compare to like modeling a standard data-driven distribution with a score function. So this is what I've seen. You just use typically neural net or some deep neural net architecture. As I said, like in production scale models, you typically have some kind of UNet architecture to model the score function. Yeah.
When you say JAX has better performance than PyTorch, do you mean like in terms of time, or?
Yeah, I think the question was like whether JAX has. I made the statement that JAX might have a better performance than PyTorch with regards either to time or memory, right? And I'm referring just to, I think you will find benchmarks done by the Keras team because they support multiple backends. So they support JAX and PyTorch. And there I think they found that like typically in terms of time, JAX has the better performance at the cost of slightly higher memory. I think this was in a single sentence like what they broke down, but the differences are not huge. So I don't have the reference right now, but I think if you search for Keras benchmarks, JAX versus PyTorch, you might find something. Okay, yeah, thanks again for the invitation, and I hope this was useful. let's get to the last and most interesting part of the tutorial. So let's make the final step towards